In this video, we'll learn about the op-amp inverting configuration. Here's the inverting configuration. It's an important circuit in its own right that's used all the time, and it's also going to give us a nice introduction into analysis of op-amp circuits. You'll remember the ideal op-amp characteristics: infinite input resistance, zero output resistance, infinite common mode rejection, or zero common mode gain, and finally, infinite differential gain, ideally over all frequencies, which we call infinite bandwidth. I'm going to spend a moment talking about this last assumption a little bit more. If we simply write the input-output relationship here, we can rearrange it to show that the differential input is equal to the output voltage divided by A. Now, if we make the further assumption that this circuit is stable, then we can assume that its output voltage is finite. If VO is finite, but A is infinite, then we must conclude that the difference between the two input voltages is zero. This important fact is going to greatly simplify the analysis of ideal op-amp circuits. It's often called a virtual short between the inputs. Or even a virtual ground, since one of the op-amp terminals is often connected to ground, though not always. So this terminology, virtual short circuit, is a little bit misleading. It's very unlike a short circuit in that no current flows here. Remember, the ideal op-amp has zero current into its terminals. It's only a short circuit in the sense that if we assume infinite gain and if we assume that the circuit is stable, then there's zero voltage difference between those two terminals. So again, that's why we call it a virtual short circuit. It's not a real short circuit. We're going to use the virtual short circuit assumption often in our analysis of ideal op-amp circuits. But keep in mind that every time we use it, we've implicitly assumed that the circuit is stable. Detailed analysis of stability is a later topic. We return now to our detailed step-by-step analysis of the inverting configuration. The steps are numbered in order with the numbers in the blue circles. So the first step is to apply our virtual short circuit assumption, which tells us that the two input terminals to the op-amp are at the same voltage, or there's 0 volts across them. So that leads to the second point, which is that the voltage at the negative input terminal of the op-amp must be ground. Again, this is the so-called virtual ground. It's a ground voltage at this terminal that's being maintained by the op-amp due to its infinite gain and the stability of the configuration. Since this node voltage is ground, we now know the voltage across this resistor. It's simply VI, since the voltage VI is applied at the input to the inverting configuration on the left. The resulting current is easily computed from Ohm's law. That's step 3. The current I1 is just the voltage across this resistor, VI, divided by its resistance, R1. Step 4 is to recognize that an ideal op-amp has 0 input current. So therefore, if we write a nodal equation here, the sum of all the currents has to equal 0, so the current flowing out this branch must precisely equal the current flowing in this branch. That is, the current in this branch I2 equals I1, which we already showed as VI over R1. The current I2 flows across resistor R2 and induces a voltage drop across it, I2 times R2. Now, if we substitute in what we know about I2, we find that that voltage drop is equal to VI over R1 times R2. The final step in the analysis is to find the output voltage, VO, which may be written as the voltage at this terminal, V1, our virtual ground, 0 volts, minus the voltage drop across this resistor, which we just found. So we substitute that in here. The result is that we find the output voltage is equal to negative R2 over R1 times VI. The gain, therefore, of an inverting configuration, assuming an ideal op-amp, is negative R2 over R1. That's an important expression that it's worth remembering. It's worthwhile to repeat the analysis, assuming a finite gain in the op-amp A. That is, in this analysis, we'll assume that the op-amp has a gain of A, but is otherwise ideal. So it still has infinite input impedance, 0 output impedance, and so on. But since we've relaxed the infinite gain assumption, we can no longer make use of the virtual short circuit assumption. So we must now find the voltage at this node V1. We can't simply assume it's a virtual ground. Well, V1 can be written in terms of the output. Since VO is 0 minus V1 times A, we can rearrange that to say that V1 is negative VO over A. And that's what's written here. Knowing the voltage there, we can now proceed to the rest of the analysis. The current I1 is equal to the voltage across resistor R1, VI minus V1, divided by the value of the resistance R1. We know the voltage V1 is negative VO over A. So we can substitute that in. As shown here. Now the op-amp is otherwise ideal, so it still has 0 input current, which means that all of that current I1 flows through this path and becomes the current I2. It flows through R2 and induces a voltage drop across it. That's equal to I1 times R2. Finally, the output voltage VO can be written as the voltage V1 minus the voltage drop across the resistor R2. Substituting in what we know about I1 into this expression, we can obtain an expression that relates VO and VI in terms of the op-amp finite gain A and the resistors R1 and R2. Rearranging this expression gives us the closed loop gain G of the inverting configuration with a finite op-amp gain A. It's a lot more complex than our expression for the closed loop gain when the op-amp was ideal and we had infinite gain, that was negative R2 over R1. But you'll see that as long as the op-amp gain A is much larger than the quantity 1 plus R2 over R1, then this term here in the denominator is very closely approximated by 0, and the whole denominator starts looking like unity, and we end up with a closed loop gain that's very close to our ideal value of negative R2 over R1. So certainly this assumption of a large gain A from the op-amp is met in the case of an ideal op-amp where A is infinite. And in that case, that limiting case, we get precisely the same result as we got for our ideal op-amp assumption. I think it's interesting at this time to think about what happens when we have an op-amp whose gain A is a function of frequency F. For example, following the plot shown here. And we just showed that in an inverting configuration, as long as the amplifier gain A is a lot larger than 1 plus R2 over R1, then the closed loop gain of the inverting configuration will be closely approximated by the ideal result of negative R2 over R1. So for example, if we were to design an inverting configuration for a gain of negative 10 volts per volt, and we were to use an op-amp with this frequency response, then we would find that it would behave almost ideally so long as the gain A remains greater than 1 plus R2 over R1, which is 11 volts per volt. That's slightly more than 20 dB. So essentially, the op-amp circuit, the inverting configuration, would behave ideally up to around frequencies where its gain dips below this value. From the plot on the preceding page, we see that that happens at around 90 kilohertz. So up to 90 kilohertz, we've got an inverting configuration with a closed loop gain close to its ideal value, negative 10 volts per volt. Beyond that, our expression for closed loop gain as a function of A would show that the closed loop gain G rolls off. We'll consider examples like this in more detail a little later. Here's an op-amp configuration that's similar but not identical to the inverting configuration that's worth analyzing. So the amplifier itself is here, and we've connected to it in this exercise source modeled by its Norton equivalent, current source of 0.5 milliamps, the source resistance of 10 kilo ohms on the left. So to analyze the circuit, assuming an ideal op-amp, we'll assume it's stable, and then that together with the assumption of infinite gain from the op-amp gives us our virtual short circuit between the input terminals, creating a virtual ground at the negative op-amp input terminal, 0 volts. So if there's 0 volts at that point, and this is the source current IS, then we know that there's 0 volts across the source resistance RS, and therefore 0 current flowing in it. So all of the source current IS must be flowing through the 10 kilo ohm resistor. That creates a voltage drop across that resistor, which is exactly equal to negative VO. That is, VO is equal to the voltage at the negative op-amp terminal, 0 volts, minus the voltage drop across the 10K resistor, which is IS times 10 kilo ohms. So therefore, we can say this configuration is working like a transresistance amplifier with a gain of negative 10 kilo ohms. By the way, another way to do this analysis would have been to take this source and convert it into its Thevenin equivalent. In which case, the whole circuit would have then resembled an inverting configuration. But that might be a little confusing because the resistance RS is really part of the source. It's not really part of the amplifier configuration. In this case, the amplifier itself is just what's over here on the right in this box. So you see that with this configuration, the virtual ground at the input of the amplifier ensures that all of the source current, IS, flows into the amplifier. So effectively, this amplifier looking in here has zero input resistance. Now that's different from looking into the op-amp itself, which of course, since it's an ideal op-amp, still has infinite input resistance. But looking into the amplifier as a whole with the 10K resistor in place, we've actually got zero input resistance, which makes it a very good trans resistance amplifier. Here's another useful op-amp configuration that's similar to the inverting configuration that we'll call a weighted summer, and you'll see why shortly. Again, if we assume an ideal op-amp, and we assume that the configuration is stable, then we've got our virtual short circuit and hence our virtual ground at the negative op-amp terminal, which means we've got 0 volts there. In that case, we can find the current in each input branch. I1 is simply the voltage across resistor R1, which is V1, divided by R1. I2 is V2 over R2, and so on. So this configuration has multiple inputs, V1, 2, 3, all the way up to Vn, and produces one output, Vo. That is a weighted sum of all the inputs, because a nodal equation here reveals that the current I must be the sum of all those input currents, I1, I2, I3, and so on, all the way up to In. And those input currents are, in turn, weighted versions of the input voltages, weighted by the resistance in each input branch, R1, R2, and so on. Finally, the output voltage is formed when the current I passes through resistor RF and produces a voltage drop across it. VO is given by that voltage drop below the voltage at the negative op-amp terminal, which is 0 volts. So VO is negative that voltage drop. Substituting in this expression for I here gives us this final expression for the output voltage highlighted in blue. And you'll see indeed it's a weighted sum of all the voltage inputs, V1, V2, and so on. We can set the weighting of each term by choosing the value of the resistances, R1, R2, and so on. Now that analysis was simple enough thanks to the ideal op-amp assumption producing a virtual ground at the negative op-amp terminal. But it's useful to consider another way to do this analysis that might be more generalizable to some other situations. And that is we can do this analysis by superposition. So the way that works is we consider each of the voltage inputs, V1, V2, and so on, one at a time, and set all the others to 0. Find the resulting output. We repeat that for each input, and then sum together the results to produce the total output voltage. So for example, if we were to complete the analysis for V1, then we would set V2, V3, and so on up to Vn all equal to 0, which is the same as connecting those terminals to ground. So the resulting circuit would look like this. V1 would appear across resistor R1, and all the other resistors would have ground at their inputs. These are all the other input terminals being set to 0. So we'll just complete the rest of the schematic here. Now, since all these other branches have 0 volts across them, there's 0 current flowing in all these other branches. So the only current flowing is the current V1 over R1 coming from input V1. Again, we've got an ideal op-amp assumption, so that ensures we've got 0 volts at the negative op-amp terminal. There's also 0 input current going into the op-amp, so all of this current flows here and produces the output VO, which is just negative that branch current V1 over R1 times RF. And that gives us this term over here in the final expression. We could repeat a similar analysis for V2, setting V1, V3, and so on all equal to 0, and proceed for all the other inputs. And for each analysis, we would get a new term here in the total expression. And then we complete the superposition by summing all those results together. As I said, the ideal op-amp makes this analysis simple enough that we probably don't need to take this approach for this exercise, but in some more complicated situations, it may make your life a lot easier.